saved my preference to start streaming on YouTube. So sorry to the YouTube viewers for the late start on this data science workshop. But we're going to start streaming on YouTube now. Someone wrote Google Search Simulator. Not really sure, not exactly sure what you mean by that, but feel free to elaborate there in the comments. Maybe that this is going to search through all the possible values that could be. But thank you for noticing that we weren't streaming to YouTube. So we'll keep moving on with this here. Now I wanted to mention, so we have array 1, right? Array 1 is this one-dimensional array. But what if we wanted to make array 1 into a two-dimensional array? And actually, there are some two-dimensional reasons why we might want to do that. For example, let's say we're working with map data. And maps are two-dimensional often, so we might want to convert into 2 dimensions. And so one way we could do that is by using the reshape command. And so if we type arr1.reshape, this is something unique to NumPy, where we can reshape our data. This is not something we could necessarily do with a list. Let's redefine arr1 to something that actually can be fit into shape 4 to 5. So maybe we need to make it into something that's 20 instead of 10. Wonder what the reason why that wouldn't work is. Let's try the other choice that I have here, which is to do this. Yeah, okay, so if you use 0, 40, and 2, you can get this data. I think maybe if we had done 21, maybe it would have worked. Yeah, not sure. Oh, it's not linspace. Okay, if we were to use linspace, maybe. Yeah, that's why. Okay. So when we reshape to 4 and 5, we get a two-dimensional array. And this is a feature that we have in NumPy that can be really useful. All right, so now we're going to practice operations, trigonometric operations on NumPy. But before we do that, I wanted to bring up the chat. Someone says, cannot open Python 3.11. You could always try to open up Python 3.7 or 3.8 or 3.9. So all these versions would be totally okay for our purposes because the syntax of Python will be the same. It might be a little hard to download those packages though. So I would try maybe doing that. There's another way you can try, which is to download through Anaconda. So let me put that in the chat as well. Anaconda is a really good resource to try. Okay, everyone. So now we're going to practice just trigonometric function. So we could do np.sine on arr1, and we get this values here. So you can see we've gone from arr1, which was up here, and now we've applied sine to that, and you can see that now we get some negative numbers, and we never get any numbers that are higher than 1. So we've successfully applied sine. And there's more to this notebook, but I actually want to move on and go on to another package. So feel free to complete this notebook on your own. And if you have any questions, send a message in the chat. But I'm going to go on to the next notebook. Okay, so we're going to now open up our SciPy notebook. And so click on Learn SciPy blank. That's going to bring you to that. Spider would also be okay. You don't need to use Jupyter Notebook. But if you use Spider, you're not going to be able to um, do this containerization thing that we're going to try and do later on. Can you repeat the libraries again? Absolutely. Let me send you a link to the libraries. So here are the libraries in the chat. Just sent them over. Thanks for pointing that out. All right, everyone. So we're now moving on to SciPy. So let's get that one pulled up. And this is the Learn SciPy blank file. And you can see that there's some interesting stuff in here. We're going to learn about optimization, which is something that is useful oftentimes when you have some data or you have a function and you want to figure out what is the optimal value. But before we get onto that, I wanted to quickly point out another feature of SciPy, which is that you can pull out a unit constant. So if we type from SciPy import constants, you can get lots of different constants from SciPy. So you can get how many meters are in a foot, for example. I think inch would work too. Yeah, so this is how many meters are in an inch. And you can do this with a lot of different stuff. If you're ever like wondering about a conversion to SI units, you should totally use this. But anyway, let's move on to optimizing a function. So optimizing a function, we're going to use a part of SciPy called SciPy Optimize. And there's lots of really good stuff in SciPy Optimize. But we're going to import minimize, which is a library, a function that is used to minimize if you give a function. So let's say we have f of x, and this is the function 3x squared plus 5x plus 12. And so we're going to try minimize, and we're going to type in f and 0. So we're going to try and find the minimum value of this. And if we know our quadratic equations, then I think the value of this, yeah, the minimum value of a quadratic equation is going to be in between the two roots. So I think it's negative b over, it has something to do with b and c. So let's try running that with our minimize function. Man, I used to know that much better, but I guess not as much anymore. You can see here we get negative 0.83. So I think if we type, yeah, hard to remember that. Let's see. We'll have to return back to that. Maybe over the break I'll remember. Does anyone in the chat know the minimum of a quadratic function? Because we can actually solve without a computer in this case. Oh, I remember now. It's negative b over 2a. So if we were to say, and this would be a, b, c. So negative b would be negative 5, and 2a would be 2 times 3. So let's see what we get. We get exactly what the machine gets, negative 833. So that means that we're working. We're doing well here. All right, so now we're going to move on to spatial data. And Actually, SciPy has some interesting libraries or some interesting methods that you can take advantage of for spatial data. So first, I'm just going to plot this. We're going to use, we're going to cheat a little bit. So I'm just going to do matplotlib. Actually, I think we can just do this. And then we'll do plt.scatter. So you can see this is kind of like randomly distributed data. And so let's say we wanted to find out how far away is this point, which is at 0 and 52. So we have the 0, 52 as one of our points. And then let's say we had another point, which is at like 80 and 30. Well, we can type these into our Euclidean distance. So we can type spatial distance, import Euclidean. And if we use the Euclidean function, it will find the distance between 2 points. And so this tells us that our 2 points that we picked out, this one and this one, they're, or I'm sorry, over here, they're 82 or 83 away from each other. So that's kind of a neat result. So you could kind of find out using any two latitudes and longitudes how far away two things are if they're close enough together. All right, so now we're going to look at interpolation. And so with interpolation, we can try what we'll call interp1D. And let's define two lists. One will just be all the numbers from all these whole numbers from 1 to 10. And the other one is gonna like kind of repeat by threes. So you can kind of see that B is always going to be 3 times what A is. But you might have a function that's much more complicated than that, and you might want to use our interpolation function. So let's generate an interpolation function between these two lists, and we use our interp1D to write this, and we use A and B, our input and our output. And then we can put into this interpolation function now whatever we want. So we could put 1, 1.5, 2.5, really anything you would like, and it'll tell us what the corresponding values in B would be. Now, when you're doing interpolation, you want to make sure that you're not going to try to compute something out of the bounds of the original list. So I could write 20, but then it gives me an error. It says new value in x new is above the interpolation range. So that's actually called that's called extrapolation. So we don't want extrapolation. We want interpolation only. Okay. So in data science in general, it's much more acceptable to interpolate than it is to extrapolate, and so it's really discouraged in a lot of the functionality. Someone says, "I never knew you could find Euclidean distance so easily. I used to write the Knoll formula for it." Yeah, so now you have a new way to do that. So I encourage you to try it out next time you're trying to find the Euclidean distance. Okay, everyone, so let's move on to statistics, and this is one of my favorite things about about our SciPy package is that you can do a lot of sort of statistical models with SciPy. You can do some machine learning models, and we're going to work on the most simple machine learning model, which is a regression model called the linear model. So a lot of people don't know, but linear regression is actually a form of machine learning. And so let's import linear regression model into our notebook. So we'll type from SciPy import stats, and there's a ton of stuff in stats. Feel free to look at that. But we have just this X data here, and you might remember that our X and Y are from up here. So let's copy them down and paste them again. These are totally randomly generated data. We looked at the plot and they have no pattern, so we should expect our linear model to do really poorly at predicting Y given X. And so let's try that. We can type stats.linregress, linregress standing for linear regression, and we type X and Y. So here's the result. We get it pretty quickly because linear models are pretty quick to run. And the slope that we get is almost 0. It's really small compared to the order of the data. So the data is on the order of 10 to 100, you know, like 1 to 100. And the slope is like less than 1 by a lot. So we can be confident that there's not much of a relationship here. And if you look at our p-value, which is a measure of the likelihood that the slope is equal to 0, the p-value says that the likelihood that there's no relationship is 76%. But take the p-value with a grain of salt, but the fact that it's so high means that it's probably not a strong relationship. So we'll go ahead and discount that one. Now let's look at A and B. I mean, you remember there's this really strong relationship between A and B, which is that A is always a third of whatever B is. So let's see if that's borne out in our linear regression. In fact, you get that. So I'm just going to delete some of these cells below. And you get slope equals 3, intercept equals 0. P-value is basically 0. So what this is saying is that it's basically impossible that the relationship between them is 0. It's just there's no relationship. So we can be pretty confident that there's a strong relationship between A and B. All right, so now I wanted to bring up some things which are also statistical in nature, and so I wanted to bring up normalize. So you could normalize your data. If you look at A, let's put a new cell here and just write A out. It goes from 1 to 10, but we can actually compute the minimum of A and the maximum of A, and then we can normalize our data. Oh, we actually have to make these into NumPy arrays for this to work. So we're going to cast those lists, kind of just convert them into NumPy arrays. You can see that now, if we use this formula down here, you can make those on a scale of 0 to 1. And this is a really useful thing to do for machine learning in a lot of cases. So you can use a function in SciPy called from SciPy.signal import normalize. And if we then type normalize A, oh, I think we type it this way. Okay, I think I'm going to have to get back to you on this one. Seems like it's not exactly how I remember it to be. But in any case, you can use this formula, and I'll get back to you on the normalize. If someone in the chat knows about that one, let me know. But this is a very useful feature to know in machine learning. So I'll get back to you on that after the break. Okay, everybody, so we've now moved through SciPy, And let's go to our matplotlib file. So you're going to go to learn_matplotlib_blank. And I'm going to share that in the tab here. Okay, everyone. So we're going to start by generating some sample data. And I'm a little off my tracks here. And so by doing so, we're going to start with X values. So let's just generate 10 linearly spaced, incremented by 1 values. And then we're going to do 4 times np add np sign of x 0.2 and np random ran 10. And so that's kind of a mouthful, and I bet a lot of you are still typing that out because you know, it takes a while to type out. But basically, we're going to apply a sign to x, and then we're going to add a noise term. And so this np.random.ran, this adds noise to our data, and sometimes it's actually useful for us to add noise. For example, in diffusion models, we're adding noise to our data to help the model learn. But actually, in this case, we're just using it to generate some like fake data. And then the 4 and the 60 are just my additions to the data to make it more similar to what I want to plot. So if we then type plt.scatter xy, you can see that we get this nice sign. It's a little bit wobbly. It's not perfectly like a sign, but it's there. And I was kind of thinking that this looks a little bit like temperature data. If you're using Fahrenheit, which is what we use in the US to mark our temperatures for the day. And so 64 or 65 could be considered a comfortable temperature for the outdoors, and that could be achieved in the daytime, and then at nighttime maybe it dips down to 58 or 56. And this would be a typical day's temperature in like the winter time where I live in California. So now that we've got this plotted, I wanted to now let you know that you can change a lot of features of your plot using matplotlib. So for one, I'd like to show you marker, which is a way to change the dots into whatever you'd like. So you can change them into triangles or stars or X's. And you can also change the color. So you could change the color from red to green and stuff like that. And those can be really good ways to just make your plot look more visually appealing. Oh no, this is not good. I keep messing this up and not sharing with you all. I'm really sorry about that. Did you let me see if I can recover. So this is the function that I made for our fake temperature data. And this is the plot here where we're going from 64 to 65 in the summer to 56 in the winter. You all are right. I'm in the zone. That's right. I'm sorry to be in the zone. I need to like maybe make some kind of buzzer that you all can press on your end. Wouldn't that be good? Maybe like a web link or something, and you all can push the buzzer, and it'll make a noise on my computer and let me know that I'm not screen sharing. So maybe someday I'll figure that out. But so anyway, you can type in these markers to put in new shapes or colors and play around with that as you like using the matplotlib documentation. You can add some titles as well, so I'm going to copy this down and we can type plt title. can give it a title, temperature versus time in Los Angeles, California. And we can give a Y label. So we're using Fahrenheit to mark the temperature. And we can say time in hours, let's just say. So you can see that we're able to sort of get that labeled. And now all of a sudden our figure is really readable and understandable. And so if we change this figure to be plot instead of scatter, because you might wonder, well, what's this plot do if we're using scatter all the time? Well, plot is going to draw a line between your data, and sometimes that can be really, really good. Someone says, I'm glad you like the sound of the keyboard. My friend got me this keyboard for my birthday, and I'm really, really glad I have it. Do you have a mechanical keyboard? Does anyone in the chat use a mechanical keyboard? I highly recommend it. Yeah, let you type really fast. You do? Yeah, that's great. Okay, well, now we're going to move on to talking about some city data. And so I'm sorry that a lot of this is very US centric. I actually think that in the future I'm going to try and adapt this data set so that instead of the capitals being state capitals in the US, they're capitals of all the countries in the world. And I wanted to know whether this relationship holds for the world's capitals. But we'll see. For now, we're just going to be working with the US capital data. And so there are 50 US states, and there are also a capital city in each state. And so these are the capitals of the cities, of the states in the capital column. And this is the area in square miles of those cities. And this is the population in thousands of people of those cities. And so we can actually place this dictionary into a data frame, which we'll use pandas. So I'm going to cheat a little bit here and use pandas, which we'll learn about. And we're going to put them into a data frame. And then we can actually plot this using a histogram. So if we just wanted to plot, let's say we wanted to plot the populations, you can see that most of the US state capitals are less than 250,000 people. And so then there are a few that have over 500,000 people, but only one that has more than 1 million, which is kind of surprising to a lot of people. But really, the state capitals are not known for being very populated. For example, New York City is not the state capital of New York. Someone says monkeytype.com. We should play. We should play. Can we all play that game? I don't know. No, we should all play Type Racer maybe. Maybe we could all play Type Racer during our break. That would be cool. I never actually played Type Racer before. Yeah, we should play Type Racer during our break for those people who want to. But if you don't want to, that's totally okay. Okay, so yeah, we'll have to do that. But let's go ahead and move on to our last section, which is pandas. And so I want you to go to Learn Pandas blank, and we're going to open up that file and examine the pandas library. And so I have this same data set here from the last one. This is a dictionary, which is a native Python data type. And we're using a data frame, which I'll just call DF. It's pretty common to call these DF. And it's an object in pandas that allows you to use a dictionary in like more amplified way with more features. So if we print out this data frame, it actually gives us a pretty nice looking table of all the different state capitals, their areas and populations. And so, you know, if we go through here, let's try looking at these columns. Oh, I didn't define the variable. So, I defined it df. So we'll just go with df for now. So you can see the columns look like this, but actually I'm going to rename these columns so that we have state capital area in miles squared and population in thousands of people, so that we can really get a good idea of the units involved in these data types. So now I wanted to just show you one more thing, which is the sort values command. And you can specify whether to sort descending, which would be true, or ascending, which is false. Or I'm sorry, I think actually the keyword is ascending. And then you can sort by a specific column. So let's sort by area. And you can see we get all of these capitals here. And you can see that Annapolis, Maryland is the smallest capital by square miles. So, and the biggest one I already know, but we'll save that for later. So those are the 4 main packages in the pandas. Oh, sorry, I didn't share that screen, but basically you can follow along with the GitHub as well. But all we did was what we did in the last notebook, was make this data frame, and you can change columns this way by making the units, and if you sort values, you can get these sorted by any column, which is pretty useful. So yeah, go ahead and go into the GitHub, and you can get the outputs by anything, of anything we've done so far. Apologies to folks because I keep forgetting to share the screen. I'm not really sure why I keep forgetting to do that today. I usually don't do that, but I guess today I am doing that a lot. All right, everyone, so now we're going to go on to our correlations. And in correlations, we're going to be in chapter 3. So let me send chapter 3 to everybody. And chapter 3 should be now posted. And we're going to open up correlations _ blank. All right, I'm going to remember to share the screen this time. I'm just saying that to myself so that I don't forget. But thank you all for your reminders. Okay, so here we are in correlations. And this is the sort of last chapter of our data science journey for today, until we go to containerization and deployment. Because really the goal is just to have introduction to data science and show you some of the tools, give you a use case, which is what we're doing now with our state capital data, and then we're going to deploy so that we can view each other's work. But let's move forward, and we're going to put in this first data cell all of the packages that we've been working with today. So we have our PyPlot, Matplotlib, we have our NP, we have our pandas, which we usually call PD, and we have our SciPy, and we're going to use that linear regression method that we talked about before. Okay, and now we're going to go back to this city data set that we analyzed. And before we go on, I want to, ask you all what you think the interesting research questions could be with this data set. So as data scientists, we're always trying to answer questions using data, form a story really with our data. And so these are some ideas I came up with, but you can test whatever you'd like with your linear models. We're going to be testing these ideas that population density of a city is relatively constant. So in other words, the population densities don't really change too much in the cities. And then this idea is basically because more area means more people. So the larger your city is, the more people can fit in there. And that's kind of the basis of the research question that I sort of came up with for today. And so we're going to do a linear model, and we're going to use this capital data that we have up here. So we'll make this capital data frame. So we get our same data table. For those of you who couldn't see through StreamYard and look at what I was doing from before. Oh, and little to no vacancy. That's true. So maybe you have a city that was very big at one point and then shrunk and had very high vacancies. And actually, we do have some cities like that in the US, especially in the Midwest, in the middle of the country, like, for example, in Lansing. I would expect maybe to see something like that, where we built a lot of buildings, but then actually people left the city over time. So that's a good thing to think about, actually. Could there be a vacancy? Basically, data science is Matplotlib, Pandas, and NumPy. So that's those are some very key core packages. But actually, there's some more. I specifically did not cover too much in machine learning, but there's a lot of machine learning packages that you can download. Most of them have Matplotlib, Pandas, NumPy as dependencies. But there's if you're interested in those, there's sklearn, and there's PyTorch. There's a bunch of things to look at. But yes, in a sense, there's a lot of things that you can do with these simple packages that we've learned today. So let's continue along and run our linear regression, and we'll do that using area as our predictor variable, and then population as our dependent variable. So we're just kind of saying that if we know area, then we can predict the population. That's kind of the idea with this model. And you can see that we get a slope that's 0.1. And looking at these data, they seem to be in the tens, in the hundreds. So really, we have a really low slope, and our p-value is pretty high. Generally, we look for a p-value that's less than 0.05 to say that there's a relationship. And here we don't get that. There's also an R value of 0.17. And if you read this, this explainer here, R values that are close to 1 or -1 are perfect correlations, nearly. But if they're close to 0, you have a weak correlation. So we're actually much closer to 0. And so our correlation is pretty weak here. Let's try plotting this data and seeing if we're able to like see what's going on here. Yeah, so it kind of looks like we have this linear trend here, but there's a couple of data points that are kind of standing out. And there's this one in particular, the one that the x value is over 2,500. That one is definitely going to drag our regression model down in its skill level because it's really such a strong outlier to our data. And actually, we can mask out that point and rerun, and we can see what the result might be. So let's try that. This is what we call a spurious, well, it's what we call an outlier, really. And so if we get rid of this one point, we might be able to see a relationship between our data. And this is kind of a common thing to try in data science. So let's try that by using a mask. So when we define a mask, this is something we can do with pandas. And we're just basically creating a set of Boolean values that will tell pandas whether to include or exclude the data in our analysis. So if we type capital data mask or area greater than 2,500, that's going to exclude this point up here, this Juneau, Alaska point, which is the only point that has this really high area value. So we're excluding data, excluding high area data. And actually, I think we should use less than for this to do that. The answer key notebook's slightly different than this, but we're basically doing the same thing. So now that we have our new data, we can apply this mask, and you'll see that in the A's here, Alabama, Arizona, Arkansas, Alaska has disappeared. Okay, so we're going to make this into like something we'll call capital data clean. This is going to be our capital data with the Alaska data removed. And if we go back and we do our linear regression again, can see that our slope has drastically improved. So now we have a slope that's kind of on the same order of magnitude as our other things. Our R value is much higher, it's almost 0.8, and our P value is almost 0. And so we have a much stronger result. And now we're going to look and see if we can get the average population density of the capitals from our regression. And the P units would be people per square area. So if we look at the slope, this is actually thousands of people per square mile. So you can actually say in US capitals, except Alaska, which would not be included in this analysis, the average population density is 1,875 people per square mile. Okay, so now let's talk about cases where we cannot perform a linear regression, and there are actually many cases. This is a very good point. This is because if you surface a topic in our discussion, there's no bad question, absolutely no bad question that you could ask. In fact, every question is going to help surface a topic and generate a discussion. So I wanted to just kind of bring that up and address that because, yeah, there's a really good point to be made there, which is that if your question can often bring up more questions or help me clarify for everybody. So these are some cases when we cannot perform linear regression. So if variation is too low in either dimension, especially in our x dimension, So for example, if we had just so many points that are very, very tightly together, that would be really hard to do linear regression on. If the residuals are not normally distributed, and what does that mean? I mean, normally distributed. Well, have you ever heard of a normal distribution? So let me show you a normal distribution. Normal distributions are kind of fun to look at. So here's a normal distribution, and it's a symmetrical distribution. It has its values concentrated in the center. And so if your data looks similar to a normal distribution, and there are tests you can do to verify that, there it is, everybody. Wanted to thank you. Thank you very much. Appreciate your help. You can see that your data would satisfy the conditions to use a linear regression model. If your residuals look this way. So let's compute our residuals and see, see if our residuals look that way. So we're going to save these values from our linear regression. So we're going to use slope, intercept, R, P, SE equals. So we're going to save all this stuff from our output, and we can use it below. So we're going to have our population, which is our regular data, our area, this is from our area column, and we're actually going to make a predicted values of population based on our model, and that's going to be the slope times the area plus the intercept. So this is our linear model at work, predicting the populations based on the area. And the residuals are our population values minus our predictions. So we can plot those residuals, and if we do so, we see that they're pretty much centered around 0 and concentrated in low values. Now, this is not what you would call a perfectly normally distributed value. Here it is, everybody. And so, but, it's pretty close. Sorry, everybody. But there it is. So you all could follow along and try and compute your own residuals. Now there's another one, which is if the data set is heteroscedastic, I should say, actually. And so what's that? What's heteroscedasticity? So let's look that up. This is something a lot of people don't think of with their data sets, and there are some ways to correct this, but it's important to think about. So let's go to this website here. So homoscedastic data looks like this, where the width, it's almost like the width of a line is staying constant. The variance of your data with respect to some possible trend line is constant. But with heteroscedastic data, we might have a changing variance over time. So you can see as we get to higher and higher values, we get increasing variation. And so a lot of folks don't realize this, but this could create a biased estimate of your error and could result in an overestimating the fit of your Pearson value, which is this R value we're looking at. So let's look at our data and see if it is heteroscedastic. So it is again. Share that with you. So if we were to plot our data, capital data mean area against our capital data mean population, let's use scatter. It'll be easier to see that. What do you all think? Do you think this looks heteroscedastic? Well, we can plot the residuals as well against this. And you can see the residuals definitely get further away as we get to higher values. So, you know, yeah, it's kind of debatable, but there's definitely a few points, at least at these higher, larger cities, that could be influencing our model. So definitely worth keeping that in mind, and maybe the goodness of our linear model to predict populations is not so simple. So yeah, definitely worth thinking about this kind of interesting problem. Okay, everyone. Well, thank you for joining for this first half. And in the second half, we're going to actually learn how to deploy our notebooks. So I wanted to ask you all to save these correlation notebooks. And then when we come back, we're going to put them on Binder. And actually, after Binder, maybe we'll have a type race. Yeah, we'll have a typing race with anybody who wants to stick around after the workshop. Because I have to look around. I have to actually have to look at the normalize method over break to clarify that for you all. So happy break, and just we'll take 10 minutes of break. everybody. I'm really excited for you to see our binder, which is going to be like a way to deploy your notebooks. But before I get to that, I wanted to ask, how was everybody's 10-minute break? Did anyone do anything interesting? Maybe I don't know, get some reading or make a drink, like a tea or something. I'm almost out of my blue drink, so I only have a little bit left. Sad stuff. Some tea, nice, awesome, good. It's always good to have a little bit of tea. Keep yourself hydrated and warm. All right, everybody. So now we're going to move on and talk about Binder, which is a way to deploy your notebook. So I wanted to put into the chat the link to Binder. Oh, I explained what my blue drink is to folks before, but let me explain it one more time. So it's a flavor that's very popular in the United States, where I'm from, called blue raspberry. And so here it is. Maybe you also have had blue raspberry before. But basically, the reason why we have blue raspberry is, oh, hang on one second, is because they wanted to make it different than all these other flavors, cherry, watermelon, and strawberry, because they were all red. So they made raspberry blue. So this is raspberry. So it's actually a raspberry flavored drink. So there you go, blue raspberry. All right, so now we're going to move on to Binder, and so you have the link in the chat. I'm also going to put a link to a wiki on this topic, and basically this is a web app for essentially for Docker, so you can connect your GitHub. You can kind of containerize this and using Docker and deploy it as a web app. And so you have your own copy, hopefully, of the Data Science Workshop repo, and that link is data_science_workshop, but you want to go ahead and put in whatever link you have for your account. And you need to write in the Git reference, so it could be a branch in this case, potentially if you made a branch, but mine is head because this is the repository. If you made a fork, I think it should also be head. And then you can make the path to the notebook file. So I'm actually going to use URL because I'm not really sure how to do that very well. Actually, I think I can do that. So let's use files. So I think we can do chapter_3. Then we will do correlation like IPy notebook. So that should bring us to the right spot. Okay, everybody. So now I'm going to click launch, and hopefully this will work on our first try. But basically what's happening in the background here is Binder is searching for our requirements.txt file that we made at the beginning of the workshop, and it's going to build a Docker image that will be based on that, on those dependencies, and then it will launch that in the cloud using Google Cloud because they have donated some space to the Docker project. You can see, I think they're actually, maybe that's not true anymore. I shouldn't say that because I know at one point it was true, but maybe that's changed since last time. But in any case, they push the Docker image into the cloud, and then you can connect to it. Anyone can connect to it, and so yeah, it's just going through its motions here. And there's this link here, so that you all can see this as well. I'm going to paste the link into the chat. So go ahead and go to this link if you'd like. And now correlation is live on the internet. And so anybody can run this notebook. And so, yeah, it's pretty neat. Weird. Let's see if it works if I just get rid of that. Oh, maybe it hasn't quite finished yet. Let's just see if a cell without the libraries runs. Yeah, so basic Python is working. Maybe the requirements.txt file has to be in the same directory. Let's do some troubleshooting here. Well, anyway, you all should try this on your own as well, and see if you can get that to work. Maybe we should build a new repo. Let's see, maybe we're just, I think maybe the requirements.txt file has to go into the same directory as what we're trying to deploy. So let's go back to Binder, and we're going to try again with maybe a simpler file. Okay, folks, this is live coding. As you know, it can be kind of difficult to get everything right when you're doing it live, but oh, that's true. You could use the pip command in the notebook itself, but you would have to do that every time. That's a really good suggestion, Siddharth, to try that. But I want to try maybe doing chapter 1, because that's where we have the requirements.txt. So let's go back to our data science workshop repo, and we're going to use chapter 1 slash you know, I actually think that the notebook file, maybe we can just exclude the notebook file. We're just not going to do that portion of it, and we'll launch. So why don't you try rebuilding just like this. Don't put a file in there. Okay, so now we can browse to chapter 1, for example, and we can go to our matplotlib folder, and when we run this, all right. Well, I think we should try, I think at this point we should try your suggestion, Siddharth, to do that. There's definitely something that I'm missing here. But let's try using the pip command. So we can install these and we'll also install matplotlib as well. Okay, that was a very good suggestion. Thank you for that idea, Siddharth. So now when we run our cells, we should be able to run the whole notebook on the web app, basically. Pretty cool. So thank you for that workaround, Siddharth. I'm gonna look into that. After the workshop, I'll publish a little message in Discord with some of the things that we've figured out along the way in this workshop for anybody who wants to review that. Someone says, how much math do you use at work as a data scientist? And I think the answer is quite a bit, especially statistics, because your job is to translate data into narratives, stories, and that can help make a decision or help understand something better. And so you need to be using the right models to interpret that data. And so you've got to understand that. But there are other types of math that you might not run into as much as a data scientist. I think statistics is definitely one of the biggest fields of math that you would use. Right. So now we've actually figured out how to run our own container in this. And someone else asked, well, Siddharth asked, what do you think about RStudio? I think RStudio is very good. And so for those of you who aren't familiar with RStudio, this is another option that you have. If you don't like working with Jupyter Notebook, Jupyter Lab, you went through our session, you said, I don't know if I like this technology, you could try RStudio. Another place that is open source technology for data scientists. But personally, I don't use RStudio that much because I think Python language makes more sense to me. Someone says Google Colab. Yeah, this is another thing we can use instead of these binder notebooks. Maybe we'll explore that in the next section, in the next session. Sure, no problem. All right, everybody. So now we're going to play some TypeRacer. I've never played TypeRacer before, so it's new to me. I hope it works well for us. But the session's over. So congratulations to you all for finishing the data science session. And now we're going to relax a little bit and play a game. So great job, everybody. Let's do some typing. All right, TypeRacer's not loading for my computer. Okay, all right. I think I got it figured out. I'm glad the session was insightful. I'm glad you liked it. And is there going to be a recording? Yes, Joseph. The Twitch will automatically record this session. So you just go into Twitch videos and you can see the whole recording. So thanks for that question. I guess I should have paused before we started type racing for some questions. But please feel free to ask any questions that you'd like. Okay, so here is the TypeRacer. So I'm going to create this racetrack and put it in there. Thank you. I'm glad you enjoyed the session. I hope everybody enjoyed the session. Okay, so here we are in TypeRacer. Really hope that. Okay. Wonder if there's a way for me to just zoom in so that there's no ads. All right, we're gonna wait for some competitors to join. If anybody would like to join, please do so. All right, we have guests in the dark blue car. Guests in the dark blue car. So I guess the idea of this is just to, we have Sid too. Oh no. Now I'm getting caught up too. Ah. Okay. So this is a quote from a Madonna song. That's really interesting. Didn't know about that. Okay, some folks want to play too. That's totally okay. You can try to beat my first place over here. Want to try again? Let's click try again. No. Maybe we should just wait for everyone to finish. Okay, I think we can wait for everyone to finish. I'm not really sure about this game. I'm not sure how to change your name either. But I think if you make an account, you can change your name. Okay, looks like we can maybe have a new race, so we can start again. All right, so we're gonna have a new race, everybody, and it's at the same URL, I think. So please join if you'd like. We have our red car. We have the Sid car. I'm guessing that's Siddharth. Not 100% sure, but let's go. Okay, I have some time to answer a question while we finish the game. So let's see. Siddharth says, a follow-up to the question I previously asked, everyone learns Python, so learning RStudio will give an advantage to a data scientist over those who don't know it. Yeah, I think you could certainly make an argument about that, because maybe your skill would be in more demand. But it's also important to know that if you use Python, you could then potentially have a little bit more ability to use some like packages that you might not normally be able to get to. Okay, let's try one more game, everybody, and then we'll stop our. Oh no, I'm getting stuck. Right, I guess 90 is about how fast I can go. But anyway, oh well, you should get a mechanical keyboard, Joseph. And maybe we should do some more type racing at Global Hack Week. What do y'all think? Huh? I think that would be pretty cool. All right, everyone. Well, thank you for joining and for your attention, and also for the great questions in the chat. Yeah, should I? I mean, all right, maybe JFK and I we should do some type racing together. Excellent. At the speed of C. You know, that could mean two things. That could mean how fast C as a language is, or at the speed of light. So, but anyway, thank you everybody for joining for this Beginners Week data science session, and I hope you have a great rest of your Beginners Week. Bye now.